Hello guys, welcome back to my YouTube channel. I'm Prakritian from Sri Venkateshwara College of Engineering. Today I'm going to present about an undecidable problem, that is RE, which comes under the subject called Automated Theory and Compiler. Contents are Introduction to Undecidable Problems, Overview of Automated Theory and Compiler Design, Definition at an Undecidable Problem, the halting problem in Automated Theory and Compiler Design, Explanation of the halting problem, Proof of undecidability of the halting problem, Implications of undecidability in Automated Theory and Compiler Design, Other examples of undecidable problems in the field, Conclusion and future directions in automated theory and compiler design. Introduction to undecidable problems. Undecidable problems are a fundamental concept in automated theory and compiler design, posing unique challenges and limitations. They form the basic of theoretical computer science and have significant implications in practical software development. Overview of automata theory and compiler design. Automata theory studies abstract machines and computational models, including finite automata pushdown and Turing machines. Compiler design deals with creating efficient and optimized compilers for translating source code into executable programs. Definition of an undecidable problem. Complexity. Undecidable problems cannot be solved by an algorithm, leading to a critical complexity challenge. Theoretical limitation. They are problems for which no computable solution exists within a given set of rules or constraints. The halting problem in automata theory and compiler design. Introduction. The halting problem is a classic example demonstrating the limits of computations in determining program termination. Applications. So it has significant relevance in compiler design and runtime error detection. Complexity analysis. The problem is undecidable, impacting program correctness and optimization. Explanation of the halting problem, program termination. The halting problem assesses the possibility of determining if a program will halt or run indefinitely. Undecidability, it showcases that no algorithm can resolve this problem for all possible program inputs. The halting problem is a fundamental concept in the theory of computation, specifically in the field of computability theory, which explores the limits and capabilities of computing machines. The problem was first introduced by the mathematician and logical Alan Turing in 1936. The halting problem is essentially concerned with determining whether a given algorithm or program will eventually halt or continuing running indefinitely. More formally, it asks whether there exists a general algorithm that, given any arbitrary program and its input, can correctly determine whether the program will halt on the input or run forever. To state it more precisely, let's assume there is a function h of p comma x that takes a program p and an input x as its arguments and returns true if p halts on input x and false otherwise. The halting problem asks whether there is a general algorithm that can compute this function of any pair of p of x. Alan Turing proved that it is impossible to create such a universal algorithm that can solve the halting problem for all possible inputs. This proof is based on a technique known as diagonalization. The key idea is to construct a program that contradicts the existence of a universal halting algorithm. Proof of undecidability for the halting problem. Gödel numbering introduces the concept of encoding programs into natural numbers for analysis. Diagonalizations, technique used to demonstrate the existence of non-computable functions within the context of the halting problem. Turing machines shows that the application of Turing machines to establish the undecidability of the halting problem. Implications of undecidability in automata theory and compiler design. Software reliability. Compilers and language design face challenges in ensuring reliable program execution. Optimization. Performance optimizations are limited by the undecidability of certain program properties. Other examples of undecidable problems in the field: post-correspondence problem, another classic undecidable problem involving sequence matching in formal language; Banach-Tarski paradox, challenges that divide between intuitive concepts and the concept of space and mathematical models. Challenges and limitations in dealing with undecidable problems. Resource allocation. Allocation of computational resource becomes a critical concern in handling undecidable problems. Algorithmic boundaries. Developing strategies to work around the undecidable problems imposes significant algorithmic constraints. Dealing with undecidable problems poses significant challenges and limitations in the realm of theoretical computer science and related fields. Here are some key challenges and limitations associated with undecidability. Absence of general solutions. Undecidability results imply that there is no general algorithmic solution for certain problems. This absence of a systematic method to determine the outcome or answer means that we cannot develop a one-size-fits-all approach to tackle undecidable problems. Limited predictability. The undecidability of certain problems implies that there are inherent limits to our ability to predict the behavior or outcomes of certain computations or decision process. This limitation has implications for various areas including program analysis, optimization, and automated reasoning. Implications for formal systems. Undecidability have profound implications for formal systems and mathematical logic. Gödel's incompleteness theorems, which demonstrate the limitations of formal axiomatic systems, are closely related to undecidability of certain mathematical problems. Conclusion and future directions in automata theory and compiler design. Research focus. Future research aims to explore the solutions and approximation techniques for undecidable problems, advanced tools, development of advanced tools and methodologies to address undecidability in realistic software environments. Thank you.